This is the section D. This is case-based questions. Let us read out the statement of question number 29th of section D. An electron with a speed v naught, that is very less than c. C is the velocity of light, moves in a circle of radius r naught in a uniform electric field. The electron is able to traverse a circular path as the magnetic force acting on the electron is perpendicular to both r naught and magnetic field B as shown in the figure. This force continuously deflects the particle sideways without changing its speed, and particle will move along a circle perpendicular to the field. The time required for one revolution is t naught. So the things that have been given here is basically a charged particle is there that is experiencing electric field and magnetic field simultaneously, and that is making the force are balancing the electron to move in a or a charged particle also that happens in cyclotron that makes to move it in a circular path, and radius can be decided by the amount of the magnetic field applied on that charge as well as the electric field that is being given. So this is the force continuously deflects the particle. It means at every step it is being deflected at an angle of 90-degree. That is why it is going to traverse a circular path. Now the time required for one revolution is t naught to complete one full circle. So we will be applying the formulas of the cyclotron that we have derived. So indirectly the derivation of cyclotron is being asked in terms of the question. In that, the first question is, if the speed of the electron is now doubled to 2v naught, then the radius of the circle changes to, and the options are given to us. Now we are taking the direct formulas of cyclotron, in which the radius that we have derived is equal to mv upon qb. The speed of the electron is doubled. Say v dash is the new speed, so that is equal to 2 times the initial speed, that is v naught. So we are having in this formula, this is the basic one, r naught v naught. This is the radius that have been mentioned to us, that is given here, the circle of radius r naught, and v naught is the velocity with which it is moving along the path, and the speed of the electron is now doubled to 2v naught. So v naught is the initial one. So the new velocity is equal to 2 times the initial velocity. So the new radius will be equal to m 2v naught over qb, or mv naught qb into 2. Rearranging, we get this result. Or r dash is equal to mv naught qb is equal to r naught. So r dash, the new radius, is equal to 2. In place of mv naught qb, we'll write down r naught. So it is 2 times the initial radius. So the answer for the first part is B, 2r naught. So answer for the first is B option, that is 2r naught. The second part, the question asked is, if v is equal to, the new velocity is equal to 2 times the initial velocity, then the time required for one revolution of the electron t naught will change to, and the options are given to us. Let us see the factors on which the time period depends. T time period is the time taken to complete one full revolution. So that is equal to the total path it has traveled in one revolution. So it is following a circular path. So the circumference is the total length that it has followed, that is 2 pi r, and this is the time, this is the length divided by the velocity. So v naught is the velocity and r naught is the radius that it is going to traverse. So t is equal to 2 pi r naught by v naught is the formula for the time period. Now the value of r naught, we know r naught is equal to mv naught upon qb. So putting the value of r naught in the formula of time period, we have t is equal to 2 pi m v naught upon v naught qb. So this cancels out and this comes out to be equal to 2 pi m qb. So if you look at the formula of the time period, it is equal to 2 pi m qb. It is not having the velocity component in it. So time period, it is independent of the velocity. So it is not going to change even if we are going to increase. If there is no change in the mass, charge and the magnetic field, the time period is going to remain the same. So since t is independent of velocity, therefore there is no change if v is equal to 2v naught. So the option C is the correct. So answer for the second part is C, t naught. The time period remains unchanged on increasing the velocity 2 times. In the third part, the question asked is, a charged particle is projected in a magnetic field and magnetic field is given 2I cap plus 4J cap into 10 power 2 Tesla. If the acceleration of the particle is found to be, acceleration is given x I cap plus 2J cap meter per second square. Find the value of x. Here, magnetic field and acceleration are given. Acceleration is related to the force. Force is mass into acceleration, and there is a relation between force and the magnetic field. Since force F is equal to Q V cross B, where Q is the charge, V is the velocity, B is the magnetic field. From here, we know force is perpendicular to magnetic field. Now, there is one more property of the perpendicular vectors. The dot product of perpendicular vectors is 0. Also, dot product of perpendicular vectors is 0. We are using two properties. First, the formula from where we conclude that force is perpendicular to magnetic field, and second thing, since force and magnetic field, they are perpendicular, so their dot product will be 0. So F dot B is equal to 0. Now force is mass into acceleration dot B, this thing is equal to 0. Since mass is a constant quantity, so it can be taken outside or of both multiplication, it is equal to 0, or A dot B will also be 0. Now I'll put the values of acceleration. This is xi plus 2j and dot 2I plus 4j into 10 power 2 is equal to 0. Like mass have been taken outside, this 10 power 2 can also be taken outside, that will become 0. So xi cap plus 2j cap dot 2I cap plus 4j cap is equal to 0. So I dot I will become 1 2x, I dot j will be 0, j dot I again 0 plus j dot j 1. So this thing is equal to 0, or x comes out to be equal to minus 8 by 2, that is minus 4. So acceleration, using this formula, the value of x comes out to be minus 4 meter per second square, because it is the acceleration component. So out of the option 4 meter per second square, minus 4, 2, minus 2 and 2, the option B is correct, minus 4 meter per second square. So for answer of third part is B, that is minus 4 meter per second square is the answer for this part. In the fourth part, if it has been asked, if the given electron has a velocity not perpendicular to B, magnetic field, then trajectory of the electron is a straight line, circular path, helical, or the zigzag. Now, if the electron has a velocity not perpendicular to B, there are two components of velocity. We have resolved velocity in its two components basically. One is in the direction of magnetic field, it remains unaffected. There is no change on it. And another one is the parallel and another is a perpendicular component. And perpendicular component of velocity follows circular path. One of the component of velocity is not affected and the perpendicular component of velocity is undergoing a circular path. So it will follow a helical. Hence, path followed will be helical. Helical path will be the followed like this. So the answer for the fourth one is the C part. Answer for the fourth is helical. Now the fourth part, this is an option or is being given a choices there. If this electron of charge E is moving parallel to uniform magnetic field with constant velocity v, the force acting on the electron is, see, we have again will have that formula, F is equal to Q V cross B. F is the force, Q is the charge, V is the velocity and B is the magnetic field. And here instead of Q, electron is being mentioned, so we'll replace it by this. Now, if the field is charge is moving parallel to uniform magnetic field, it means E V B sine 0. In the parallel means angle will be 0. So the force acting on the electron, sine 0 is 0, so this comes out to be 0. In case of parallel, it have been asked, if anti-parallel is asked, again the angle will be 180 degree, the force will be 0. So the electron moving parallel or anti-parallel to uniform magnetic field, the force acting on the electron is 0. Here parallel is being asked and we have found out this answer. So D is the correct option for this, and the answer for the fourth part is D, that is 0. Now the 30th question of section D. It is the phenomena of emission of electrons from a metallic surface when light of suitable frequency is incident on it. The emitted electrons are called photoelectrons. Nearly all metals exhibit this effect with ultraviolet light, but alkali metals like lithium, sodium, potassium, cesium, etc. show this effect even with the visible light. It is an instantaneous process. Instantaneous process means it starts as the light is being incident and the photoelectrons are to be emitted, this process starts side by side. That is, photoelectrons are emitted as soon as the light is incident on the metal surface. The number of photoelectrons emitted per second, in 1 second, the numbers of electrons that are emitted is directly proportional to the intensity of incident radiation. So here the photoelectric effect is described in the question number 30th. Continuing with the theory that have been given to us in the 30th question, the maximum kinetic energy of the photoelectrons emitted from a given metal surface is independent of the intensity of incident light. It is not depending on the maximum kinetic energy of photoelectrons that are emitted. That is not depending upon the intensity of incident light, but it depends only on the frequency of the incident light. Intensity is not concerned here, the frequency is concerned, and every metal surface there is a certain minimum value of the frequency of the incident light, that is the threshold frequency, below which emission of photoelectrons is not occur. Like we are having fingerprints that are different from others, so every metal is having a different threshold frequency, a minimum frequency, and the incident light below which there won't be any emission of the photoelectrons. So in this part it have been asked, in a photoelectric experiment, plate current is plotted against the anode potential, and these are the options given to us, A and B. You can see the curve, this is the anode potential and I is the plate current. Three curves A, B and C are being shown. In this, the question have been asked, A and B will have same intensities while B and C will have different frequency, or B and C will have different intensity and A and B have different frequencies, and C and D are the options given. So don't get confused with the things, you just go to the concept, and according to the concept, this I, plate current, this gives the information about the intensity of incident light. And intensity of incident light, it is a measure of number of photoelectrons emitted. This is the first concept. This is about the I, that is the plate current along the y-axis. And second concept is that the anode potential, called as a stopping potential also. Stopping potential gives the information about frequency of incident radiations. Now, when we are clear about these two things, we can answer this question. See here, this A and B curve, they are having the same saturation current. If the saturation current is same, it means they are having the same intensities of the incident light. Second thing is there, that B and C, these are having the different anode potential, and anode potential is giving us the information about the frequency. So B and C, because they are having the different anode potential, they will be having the different frequencies. And A and B, since saturation current is same, so they are having the same intensity. So this is the concept that we have got from these two facts. So we will be having A and B are at the same intensities, and B and C will be having the different frequencies. So let us see. A and B will have the same intensities. This is how we have mentioned. And B and C will be having the different frequencies. Yes, it is so. Since this plate current gives the information about the intensity of incident light. Since the saturation current in A and B, should I write it? A and B, as we see from graph, have same saturation current, so same intensity. B and C are at different anode potential, and at anode potential gives us the information about the frequency of the incident radiation. So since they are at the different points, so different frequency. So let us see which one matches this. A and B have same intensities, yes, because they are having the same saturation current. B and C will be having different frequency, yes, because their potential is different. So option A is the correct one. So the answer for the first part is A. In the second part of the 30th question, it have been asked, photoelectrons are emitted when a zinc plate is A part heated, B part hammered, C part irradiated by ultraviolet light, or D part subjected to high pressure. Here zinc plate is a metal plate here, and from which photoelectrons are needed to be emitted. So whenever we are talking about the emission of photoelectrons, we need the radiations of suitable frequency. Suitable frequency means minimum threshold frequency that is required. When that goes above the threshold frequency, the photoelectrons start emitting out. So heated or hammered won't work here. Subjected to high pressure, again that is not required. It should be irradiated by the ultraviolet light that is suitable for the zinc plate to emit the photoelectrons. So option C is the correct, and the answer for the second part is C, irradiated by ultraviolet light. See, these are the study based questions. So in that study also this thing have been mentioned that alkali metals, they emit the photoelectrons even at the visible light. For other, generally we need the ultraviolet rays. Now in the third part, this have been asked, the threshold frequency for a photoelectric effect on sodium corresponds to a wavelength of 500 nanometer. Sodium is an alkali metal and 500 nanometer lies in the visible range, so it is sufficient for it. We have to find out the work function out of these options. So we are having the formula, the phi work function is equal to h nu, and here the wavelength is being given to us. So nu is related to wavelength by the relation c by lambda, where nu is frequency is equal to velocity of light upon the wavelength. This is the formula that I have applied here. Now the h is Planck's constant, the value is 6.63 into 10 to the power minus 34 joule second, and C is 3 into 10 power 8 meter per second, and lambda is given to us 500 nanometer. So let us convert in the meter and put these values. So phi is equal to 6.63 into 10 power minus 34 divided by 500 into 10 power minus 9, and this value comes out 3.978 into 10 power minus 19 joule. So this is nearly equal to 4 into 10 power minus 19 joule. So let us see the option. So the answer matches with the first option, and the answer for the third part is A, 4 into 10 power minus 19 joule. the value of HCON will be given to you in the beginning of the question paper. In the fourth part of 30th question, it have been asked the maximum kinetic energy of photoelectrons emitted from surface when photons of energy 6 electron volt on it is 4 electron volt. So surface photons energy, their energy of the photons is 6 electron volt and the maximum kinetic energy is 4 electron volt. The stopping potential is, so let us see the relation between the kinetic energy maximum is equal to EVS, where E is the elementary charge on electron and Vs is the stopping potential. So in the question we need to find out the Vs, stopping potential. This thing is equal to kinetic energy by E, and the kinetic energy is given to us 4 electron volt upon E. So this comes out to be 4 volt. So the stopping potential comes out the 4 volt, that is option number B. So answer for the fourth part is B, 4 volt. There is a choice in the fourth part of 30th question, and in that choice part, that question asked is the minimum energy required to remove an electron from a substance is called its, so we know that from our theory that is known as the work function. So the option A, work function, is the correct answer for this. So answer for the fourth part is A, according to which work function is the minimum energy that is required to remove an electron from its surface.